Hi, I'm Henry Gilliland, an automation specialist at ES&E. In this video, I'm going to explain the purpose and usage of the MAG instruction using ladder logic in Studio 5000 Logix Designer. The MAG instruction is perfect for electronically coupling two axes together. Before we go further, I recommend you start by watching the Integrated Motion Basics overview video prior to watching this video if you haven't done so already. That video explains how motion instructions operate in general. A link to the video will be provided in the description below. MAG stands for Motion Axis Gear. This instruction is used for various applications that require two or more axes to move together in a synchronized and linearly proportional manner. One example of this is when two servo motors need to work together to perform the same task. Usually, these tasks require a high level of synchronization, and they are often even mechanically coupled together, which means that if things don't line up right, something will break. Let's dive in and take a look at the instruction. At first glance, it seems like a daunting task because there are several parameters to fill in. However, this is really a pretty basic instruction with a few basic configuration parameters that allow a high degree of flexibility while still being very straightforward. First off, because we need to tie two axes together, there are fields for both a master and a slave axis. This is a leader-follower relationship. In other words, the slave axis will be tied to the master axis and will follow all the movements of the master. However, the slave will follow according to the parameters defined in the instruction. Next, there is a motion control field. This is a field for a tag of type motion instruction. This is a tag that is used by the instruction itself to perform its task. Next, there is the direction field. This field is used to define the direction the slave axis will move relative to the movement of the master axis. 0 means the slave axis will move in the same direction as the master axis. 1 means the slave axis will move in the opposite direction of the master axis. 2 means the slave axis reverses from the current or previous direction of travel regardless of the direction of the master axis. 3 means the slave axis will continue to move in the direction it is currently moving or was moving during its last movement, regardless of the direction of the master axis. Next, there is the ratio field. This field allows the user to directly enter a value of type real that will define the proportional relationship between the master and the slave movements. For example, if a value of 2 is entered, then the slave axis will move 2 position units for every 1 position unit that the master axis moves. If a value of 0.5 is entered, then the slave will move 1 position unit for every 2 position units that the master axis moves. Next, there are the slave counts and master counts fields. Because it is sometimes desirable to enter the proportional ratio in the form of a fraction, these fields allow for that. For instance, in the case of a repeating decimal ratio such as 1/3. So in this example, if slave counts has a 3 in it and master counts has a 1 in it, then the slave axis will move 3 position units for every 1 position unit that the master moves. The ratio format field is used to select between these two different types of ratio entries. To select the format, simply select from the two options in the drop-down menu. If the ratio field is used, then the ratio format field must be set to real. If the slave counts and master counts fields are used, then the ratio format field must be set to fraction slave master counts. Note that the fields associated with the format that is not being used will be ignored. However, these fields must have values in them in order for the instruction to compile. You can just put zeros in these fields when you're not using them. The next field we will discuss is the master reference field. This field designates which master axis position reference the slave will follow. If this field is set to actual, then the slave axis motion is generated from the current position of the master axis as measured by its encoder or other feedback device. If this field is set to command, then the slave axis motion is generated from the desired or commanded position of the master axis as calculated by the motion planner. The last three fields are clutch, accel rate, and accel units. The clutch feature of the MAG allows the user to ramp the slave axis up to gearing speed at the instruction's defined acceleration value. If not enabled, the slave axis immediately locks onto the master axis. If the master axis is currently moving, this condition results in an abrupt, uncontrolled acceleration event of the slave axis, which can cause the axis to fault. Therefore, it's recommended to use the clutch feature for applications that require engaging the gear while the master axis is already in motion. Next, you will see there are 4 status indicator bits. None of these bits tell you anything about the target axis. They're only status bits associated with the given instruction. The EN or enable bit is true when the rung that the instruction is on is true. The DN or done bit is true when the instruction executes successfully without errors. The state of the done bit is only updated when the enable bit transitions from false to true. The ER or error bit is true when the instruction executes with errors. The state of the error bit is only updated when the enable bit transitions from false to true. The IP or in process bit is true when the instruction is currently executing its task. In this case, the IP bit will be true as long as the MAG instruction is electronically linking the slave axis to the master axis. Now let's build the MAG instruction in ladder logic and implement it. You can find the MAG instruction in the Motion Move tab of the instruction selector. First, assign the target slave axis and the master reference axis. Next, create a tag of type motion instruction in the motion control field. It's a good idea to name the instruction tag after the instruction you're using. This way it's easier to find when you need to troubleshoot the instruction later. Next, select a direction setting from the 4 options we discussed earlier. For this example, we will use 0 for the same direction. Next, enter the ratio you would like to use in either a real or fractional format. For this example, we will use a real format and enter a value of 1 for a 1-to-1 ratio. We will enter zeros in the slave counts and master counts fields because we're not using them. We want our slave axis to follow exactly with what the master axis is actually doing. Therefore, we will select actual for the master reference field. This means the slave will follow along with the encoder of the master axis and continue to follow even if the master axis moves while it's disabled. For the ratio format, as stated a moment ago, we will select real. For clutch, we will select enabled. Then we will select 360 and units per second squared for accel rate and accel units. This means the slave axis will ramp up to gearing speed at a maximum acceleration rate of 360 degrees per second every second, or 360 degrees per second squared. The reason we know that our units are degrees is because that is how our example axis is scaled. Make sure you know what the scaled units of your axis are before programming any move instructions targeting that axis. Now compile the code and let's test it out. In order to execute the MAG successfully, the slave axis must be in the running state. You can transition the slave axis into the running state by executing an MSO instruction. Now we can run our MAG. You can see that the enable bit turns on when the rung goes true. You can also see that the done bit turns on, indicating that the instruction executed successfully. Finally, you can see that the IP bit is on, which tells us that the MAG is active and the slave is following everything that the master is doing. Now let's test out our clutch feature. First, we have to disengage our gear. To do this, you can execute an MAS instruction of type gear on the slave axis. This will decouple the slave from the master. To confirm that the gear is no longer active, you can look at the IP bit to see that the MAG instruction is no longer in process. To test out the clutch feature, we will need to engage the MAG instruction on the slave while the master is already running. Let's run an MSO on the master axis and then an MAJ instruction to jog continuously in one direction. Now we will engage our MAG instruction. You will see that the axis slowly ramps up to speed until it matches the speed of the master axis. Now you know how to use the MAG instruction and how to build it in ladder logic. If you have any questions, please contact your local ES&E account manager or automation specialist. Thanks for watching.